so a few pointer accesses basically. And if you want to draw it, you go through that array in reverse, which is, from back to front, and you paint the triangles as you go through the lists. The PS1 actually had support to go through such linked lists in hardware. So it was meant to do this ordering table stuff. And this is basically the simplest way possible to do that sorting, because actually you're not sorting at all. You have a simple ordering table. In this example, I use 256 entries. In practice, you'd probably want more, depending on how many triangles you have. And to clear that ordering table, you just set it to 0, which is simple. If you want to insert a triangle, you just scale that to your Z range and make sure it's one of, in the range 0 to 255, and then do a linked list insertion at that point in the ordering table. And that's all there is to it. And if you want to paint similarly, you just go through the ordering table in reverse and draw all triangles in this list. So what will happen is that, you have basically just changed everything down to 255 or 256 different Z values, and you just put polygons into the ordering table at the corresponding point, and then you can just go through those elements, back to front, and make sure everything is drawn approximately correctly. So this is not perfect, but it's, again, very nice if you can get away with it. Again, this will give sorting problems, especially if your ordering table is too small. But for example, on the PlayStation 1, you had no chance anyway. And for example, if you want to approximately sort your polygons front to back, or your objects, which is a thing that's usually advised in optimization manuals for current graphics cards, because, they have some logic to throw whole parts of objects away if they're completely behind stuff that's already being drawn. And, if you want that to work efficiently, you have to make sure that the stuff, the polygons, the objects that occlude other objects are drawn first. So you have to sort approximately front to back. This is obviously not crucial. This is perfectly sorted, so you don't need to do a full sort. And ordering tables are perfect for that. You don't even need many elements. What you shouldn't use it for is to sort translucent polygons. Because when you have alpha blending, you need to sort the polygons. Basically, you need to draw them in the right order, because else your blending will be incorrect. But it turns out that all types of phase sorting, no matter how you actually implement it, are impractical on current GPUs. Because, no matter how you sort your faces, you'll always end up with a list of individual faces to paint, and you'll just have groups of, say, 3 or 4 triangles to paint, then a material change, some matrices change, then you paint another 4 or 5 triangles, and then you have to do all that changes over again. So no matter how you do the face sorting, all those changes and all those updates are basically going to kill you. So you shouldn't use that. And we have a nice solution called render passes. This is not a standard name, not something you have to know, but Chaos will explain it in this seminar later this day. So if you're interested in that, you should probably check it out. And it turns out that ordering tables are an application of a general strategy to sort called bucket sort. I'll explain that. And you throw your data into buckets based on some ordering. Say you have, for example, a set of 1,000 letters, and each of them has a colored bar, say red, yellow, orange, whatever. And you want to sort those documents based on their color, because it has some relevance. Now, one thing you're not going to do, you're not going to put those 1,000 documents on a long table, start picking a random element and doing quick sort by hand. This is not going to happen. What you really do is make a few stacks, one for each color, and just take those papers in order and just throw them onto the relevant stack. And by the point you've just thrown all those papers onto the right stack, you have one stack for each color, and this is what you wanted. And this is basically bucket sort. And afterwards, you can sort the elements of each bucket individually if you have some further sorting criterion you want to do. And that's all there is to it, basically. But if you don't want any further sorting than that rough criterion, you just don't. For example, in the ordering table example, we didn't do any sorting on the elements inside the ordering table because we didn't care about a really correct ordering. We just wanted something that was going to be approximately okay. And then afterwards, you traverse all your buckets in the correct order. Say in your colors, you have some predefined order, whatever, and you go through them, and you just pack those, stacks of papers onto each other, and then you have your final sorted list. And this obviously only works when you can calculate your bucket index, the bucket you're going to throw your data in quickly. Because if you need to perform some complicated stuff to find which bucket to put things into, this is not going to help you much, because it's probably going to be slower than any comparison-based algorithm. But it turns out that it's no problem usually for, say, numeric data or strings, because, well, numeric data, it's usually just some multiplying and whatever division to just scale it into the right range. And for strings, you can just use the characters directly. Those are 256 distinct values if you use 8-bit characters, so no problem. Those turn out to be the most important types of data, so you usually get some nice improvements with that. And if you do that repeatedly in the right order, you can actually make a proper sorting algorithm from that can sort arbitrary data and will always return a correct sorting, which is called straight radix sort. Now, this is not something I'm going to talk about in this seminar anymore, because, well, this is already the fourth algorithm we discussed, and it's pretty much enough for 45 minutes. But I'll prepare a small website with some references to the stuff if you're still interested. This will be on my homepage, which URL will be posted now. And you can look up some articles in radix sort if you're interested in how that works. Yeah, that's it. Any questions? Yeah. What? Yeah. Yeah, you can use it with constructors, but the problem is that you can't call destructors properly. Yeah, but the problem is, the question is, that I can basically use a stack-based allocator with constructors and destructors. Because I can call the constructors while allocating. Well, the problem is, by the point we deallocate, we don't know in which order things were allocated. So I can call the destructor for the first object I allocated, but I don't necessarily know its type or size. So I don't know where to advance then. Yeah, I can overload that stuff, but I still need to keep some bookkeeping information to know on what data I have to call the destructors. I can't just call that for every byte. I need to know the type and the size to call the destructor. Yeah, but that's extra information I have to keep. I can obviously do this, but this is not a simple strategy. This is really meta information I have to keep. Yeah, you can already fix that up. I mean, this is the way it works with other memory allocators. They also don't have any further type information, but you really need to keep care of such things if you want to do it in a general case. So this is not as simple as the stuff I already explained. Yeah, any other questions? No questions at all? Okay, thank you, Fabian. Yeah, okay.